Dominating set and distributed algorithms. Recap of previous lecture, we have discussed Hamiltonian graph, traveling salesman problem and NP completeness. Content of this lecture, we will discuss dominating sets, connecting dominating sets and distributed algorithms on graph. Preliminaries. Given a graph G, two vertices are independent if they are not neighbors. For any vertex V, the set of independent neighbors of V is a subset of V's neighbors such that any two vertices in this subset are independent. For example, let us say this is the vertex V, it has the neighbors, let us say U and W. So, U and W, they are independent neighbors. Why? Because there is no edge connection between them and they are independent. So, hence for any vertex V, the set of independent neighbors is a subset of the V's neighbor such that any two vertices in this subsets are independent. U and W, they belong to the neighbor of V. Now, let us see another definition. Independent set S of G is a subset of set of vertices such that for all vertices U and V in S, they do not have any edge between them. That means such that let us say U and V, they are in S and also U and V, they do not have an edge in G. Then that set of vertices is called independent set. The maximal independent set, if the vertex not in S has a neighbor in S. For example, so that means the maximal independent set means S is an independent set, is maximal independent set when the nodes which are in V minus S must have neighbor in S. For example, let us take a simple graph. If this is the graph, then let us say take the independent set which are shown by the green color vertices. So, together these two vertices are maximal independent set. Why? Because the nodes which are not green or which are not in the maximal independent set are having the neighbor in this particular set. For example, this node is a neighbor, this node which is not in S is also a neighbor, this node is a neighbor of both the elements in the independent set. So, this also should be in the independent set. So, this also node is a neighbor and this particular node is also a neighbor and this node is also a neighbor. So, these three set of vertices is an MIS. Now, this particular node, if it is present, then they are not independent. Let us not take this particular node, let us take some other node in the independent set. Let us take this particular node in the independent. So, all the green color nodes are in the independent set because they do not have any edge between them, and all other nodes are basically the neighbor of the other set. Hence, this is an independent set example. So, we have shown the independent set example. Now, the dominating set D of G is a subset of V such that any node not in D has at least one neighbor in D, and let us consider the independent set. Same example, if we construct then these particular three different set of nodes is the dominating set. Why? Because all other nodes which are not in D, that is, this is a neighbor of at least one node in D. Similarly, this node also is a neighbor of at least one node in D. This is also a neighbor of at least one node in D. So also this node and this node. Therefore, D is the dominating set, and this D is a subset of the vertices of G such that the nodes in V minus D is the neighbor in D. Now, if the induced graph of D, if the induced subgraph of D is connected, then D is called the connected dominating set. For example, here the induced graph of D is also connected, therefore it is a connected dominating set. Now, among all CDSs connecting dominating set of a graph G, the one with a minimal cardinality is called minimum connected dominating set. Now, find out a minimum connected dominating set in a given graph requires to explore the large amount of solution space. Hence, the problem of finding the maximum or a minimum connected dominating set is basically NP hard. If, let us say, an algorithm is developed to find out a minimum connected dominating, that becomes an NP hard problem. Now, let us take an application of dominating set, and that application we can find in the wireless communication and also the wireless ad hoc networks. Let us see how this particular dominating set in a graphs are used in constructing the algorithms for wireless networks. So, the idea of virtual backbone routing for ad hoc wireless network is to operate routing protocol over a virtual backbone. Because there is no infrastructure in ad hoc network, so the routing is to be done, if it is in a systematic manner without too much of communication, then it requires to create a virtual backbone and operate the routing protocol over it. That is the method. Now, here one purpose of virtual backbone based routing is to alleviate the problem which is called a broadcast storm problem. That will arise if the destination is not known. So, the source who want to send the information has to depend upon the flooding, and the flooding will create the serious problem which is called a broadcast storm problem. Thus, the construction of a virtual backbone is very important in the wireless networks to operate the routing protocol without suffering from a broadcast storm problem. So, in this lecture we will focus on the virtual backbone creation, which is nothing but is approximated by a minimum connected dominating set, and the kind of graph which we will assume for ad hoc wireless networks is called a unit disk graph that we will explain. Now we will take up an algorithm to solve the minimum connected dominating set, which will be used for construction of a virtual backbone. Now this particular problem is through the algorithm becomes NP hard problem. So we will look upon the different algorithms which are the approximation algorithms. We will look into that particular algorithm to see how the algorithms are designed, and these algorithms are distributed algorithms. Why? Because the nature of the ad hoc network is large number of nodes which are deployed, and it cannot be done in a centralized manner. So the algorithm has to be a distributed algorithm. So the distributed approximation algorithm we will discuss, and the performance ratio is 8, and that performance ratio means that it takes the guarantees of the algorithm, how much it can deviate from the optimum size of the minimum connected dominating set. So let us see that sensor network is also a network. Sensor network is also a wireless network, and we can view it as an ad hoc network. So ad hoc wireless and sensor network has an application in emergency search and rescue operation, decision making in a battlefield, data acquisition operation in inhospitable terrains, etc. It is featured by a dynamic topology. Here in such applications there is no possibility of establishing the infrastructure and operate the wireless communications, hence it is a dynamic topology wherein the infrastructures are dynamically created on the fly on demand. Now it is also featured by the multi-hop communication, and it is also having a limited resources, that is the bandwidth, CPU and battery are all limited in nature, and also such networks are having a limited security. So these characteristics puts a special challenges in routing protocol design, and hence they are inspired to create a virtual backbone. Why? Because there is no possibility to create a physical backbone, but only the inspiration of a physical like backbone, as if we have seen in the wired network, is very much required to be created. So many researchers, they have proposed the concept of a virtual backbone, and that particular virtual backbone will be used for different kind of communication, for example unicast communication, multicast, broadcast kind of communication in ad hoc wireless networks. The virtual backbone is mainly used to collect the topology information for the route detection. So it also works up as the backup when the route is unavailable temporarily. An effective approach based on overlaying a virtual infrastructure, which is also called as a core on an ad hoc network, becomes a popular. So routing protocols are operated over the core. Route request packets are unicasted to the core nodes, and a small subset of non-core nodes are also used up in this broadcasting or a routing of the information. Here no broadcast is involved, and only the nodes in the core, they are involved in the communication. The classification of routing protocols we can do in two categories: proactive and reactive routing protocols. Proactive routing protocols ask each host or a many host to maintain a global topology information. Thus a route can be provided immediately whenever it is required, but large amount of control messages are required to keep each host updated for the newest topology changes in proactive routing protocols. Now the scenario where there is a scarcity of the resources and also there is a change in the infrastructure, there is no infrastructure. In those scenarios like wireless ad hoc networks, proactive routing protocol becomes a costlier affair to maintain the information by sending all the time information whenever there is a little change, rather than another way of handling the routing protocol is called reactive protocols. Reactive protocol have a feature which is called a on demand. So a host computes a route for a specific destination only whenever it is necessary, and hence it is called reactive routing protocols. So topology changes which do not influence the active routes do not trigger any route maintenance function. Thus the communication overhead is lower compared to the proactive routing protocols. So on demand routing protocol attract much attention due to their scalability and lower protocol overhead, but most of them uses the flooding for the route discovery. Why? Because the destination is not known, so they have to basically depend upon the flooding for the route discovery. Flooding will have the disadvantage that it suffers from the broadcast storm problem. So broadcast storm problem refers to the fact that flooding may result into an excessive redundancy, contention and the collision. This causes high protocol overhead and interference to the ongoing communication sessions. On the other hand, the unreliability of a broadcast may obstruct the detection of the shortest path, or simply can't detect any path at all even though there exists one. Now in this lecture we will study the problem of efficiently constructing the virtual backbone for ad hoc wireless networks. The number of hosts forming the wireless backbone must be as small as possible to decrease the protocol overhead. Hence the core has to be of the smallest possible size. So the algorithm must be also efficient due to the resource scarcity. Therefore we must basically model this virtual backbone as the connected dominating set to approximate the virtual backbone for the wireless. So we will see how we can construct the connected dominating set using the distributed algorithm, which will be useful to create the virtual backbone for such applications. So let us take the assumptions. So we assume that the given ad hoc network instance will contain n hosts. Now each host is in the ground. That means these hosts can be dropped from an unmanned aircraft, and when it reaches the ground it has an antenna mounted on it that is a omnidirectional antenna, which will be useful to communicate and establish the network. Thus the transmission range of a host is assumed to be a disk. We further assume that each transceiver has the same communication range, that is R. Thus the footprint of an ad hoc network is nothing but a graph which is called a unit disk graph. Now in graph theoretic terminology, the network topology we basically will assume is nothing but a graph where V is the set of all hosts and E consists of the transmission links, or when they are able to communicate with each other. So a link between the two nodes U and V exists if their distance is at most R. So in real world the scenario is quite different, but for our study of the algorithm design we will assume that distance, if it is at most R, they are basically established a link between the two nodes. Also we will consider that the links are bidirectional, that is if U is able to communicate to V, so V also is able to communicate, hence the link is bidirectional between U and V in our model. Now let us see the scenario how basically the sensor nodes are dropped by an unmanned aircraft, and once they will settle down using their omnidirectional antenna, they may be able to communicate, hence they will form a graph which is called a V comma E. So V is the set of nodes and the edges between these two nodes, that is between U and V, is an edge. in a graph if the distance between u and v is at most r. R is the maximum transmission range. This graph we call it as the unit disk graph. The graph which is formed here after the deployment of the nodes, this particular graph is called a unit disk graph, and they will operate for a particular application on the field. So, we will see the existing algorithms which will construct the minimum size of connected dominating sets, which are compared on different parameters such as the cardinality, that is the size of the connected dominating sets, how much is basically how many nodes are involved. Then how many messages are required to establish the algorithm and how much time is required to establish the algorithm. The messages which are exchanged, what is basically the maximum size of them, and also basically the knowledge, the local knowledge which is required in the algorithm design, that is called the information. So, information up to 2 hop is required, sometimes it is 1 hop is required. So, the little the information is required, it will be better for the algorithm. So, here we will assume that we will see that this algorithm we will study, which will have the information which is required is 1 hop information, the message length is of the order big O of delta, and the time required is big O of n delta, and the total messages required is of the order n, and the approximation is 8 approximation algorithm which we are going to discuss. Now, computing through an algorithm the MCDS, that is minimum connected dominating set, in a unit disk graph is NP hard. Note that the problem of finding an MCDS in a graph is equivalent to problem of finding a spanning tree with a maximum number of leaves, and here the non-leaves nodes in the spanning tree will form the MCDS. And MIS is also a dominating set. Now, for a graph G having an edge, if and only if the length of the edge is less than or equal to 1 or at most 1, then that particular graph is called a unit disk graph, that we will assume in our discussion. Let us take the example how the unit disk graph is being formed. So, a node is at the center and it is able to communicate in this range, and that range is R, which is fixed for all the nodes to communicate. So, if this is the node, this is his communication range. If this is another node, its communication range is overlapping with this previous node's communication range. Hence, there is an edge. Why? Because this particular disk is of only 1 unit length, hence they are able to communicate with each other and there exists an edge in the unit disk graph. So, the topology of a wireless ad hoc network can be modeled as a unit disk graph, which is nothing but a geometric graph in which there is an edge between the 2 nodes if and only if their distance is at most 1. Similarly, we can see that there is an edge between these 2 nodes, these nodes and these nodes. So, if we finally see that this particular wireless network can be modeled as a graph, and this graph is called a unit disk graph. So, from now on we will not call it as a unit disk graph, we will just call it as a graph, and the graph we can obtain from wireless ad hoc networks. And on this particular network we have to find out the connected dominating set, minimum size connected dominating set. For example, in this particular graph, if we can see what is the minimum size of connected dominating set, we can take an example that here this particular node, if we pick in a CDS and this node also in the CDS, then this will become an independent set. Why? Because all the nodes, they are independent, and all the nodes are which are not there in this particular set, they are the neighbors of at least one of these nodes. For example, this node is the neighbor of both the nodes. Hence, this particular blue one, they are nothing but they are the MISs, or it is also called the dominating set. So, these set of nodes are the dominating set together. But they are not connected. To connect them, we can use this node also to be included, and if that is included, then the size of the connected dominating set comprises of 3 nodes. So, if the 3 nodes are taken into an account, then this will be a dominating set, and since the induced subgraph induced by this dominating set is also connected, hence it is also a connected dominating set if the 3 different nodes are taken into an account. So, through the algorithm we have to find out the connected dominating set of the minimum size, and that will be our problem in this particular lecture. Let us see some of the estimates that the algorithm which we are going to discuss is an approximation algorithm, and what is the performance guarantees of this algorithm. For that, there are some backgrounds. So, the lemma says that the size of any independent set in a unit disk graph is at most 4 opt plus 1. For that, let us see the picture. Now, here this particular node Vi is having the transmission range, and another node V that is able to communicate with Vi is having this communication range. So, if all the nodes can be connected through a tree, and we can list the nodes in some order of the traversal of this particular node. So, if let us say in that order these 2 nodes we have picked up, this particular node which is shown as the green color is able to communicate in this particular range. Now, there can be at most 5 different independent nodes. Independent nodes means they are not able to communicate. So, 5 are there. Now, if they overlap, then this will basically give a 5 the nodes, and these are this particular space is overlapped with the previous space. Now, we will count how many maximum number of independent nodes can be the neighbor of Vi, or it can be lying in Ui set. Let us say this node, this node, this node, and so on. These nodes, all 5 nodes cannot be, all 5 independent nodes cannot be positioned here in Ui. So, with this information, let us see this particular fact. Let U be an independent set of V, and let T prime be the spanning tree of an opt, that is the optimal size of connected dominating set. Now, consider an arbitrary pre-order traversal of T prime given as V1, V2 and so on up to V opt Ui be the U1 be the set of nodes in U, they are adjacent to V1. for any node I which is basically more than 2 but less than opt, let ui be the set of nodes. In U they are adjacent to Vi, but none of the other nodes. So we will take only these two nodes that we have shown in the picture, and let us find out that this will partition these nodes into U1, U2 and so on, the partition of U. So V1 is adjacent to at most 5 independent nodes. So the size of U1 is basically at most 5. Now for I is more than 2, that is the second, this is U1. So all 5 we have included, there can be 5 different nodes, this is V1. Now we will include V2 which will communicate with V1, and this particular portion we have to count how many more nodes can be there. So this is at most 240, hence the coverage range of node Vi will imply that Ui must be less than or equal to 4. Hence the maximum independent set in this particular Ui, if we count, is nothing but 4 times this is an opt minus 1. So that comes out to be 4 opt plus 1. Hence the size of the independent set, maximal independent set, is nothing but 4 opt plus 1. Having proved this particular lemma, we will see that the algorithm which we are going to discuss requires at most 4, the size of the MIS is 4 opt plus 1. Now here we will show that the minimization algorithm, the approximation is nothing but is a ratio, performance ratio, which is called, is nothing but a supremum of this particular factor ai upon opt of I. That means ai is the output size of CDS and opt is the optimal size of that particular problem instance I. So for all instance of the problem we have to find out the supremum, that becomes the approximation algorithm guarantees or the performance ratio. Let us see the algorithm, which runs in 2 phases. The phase 1 will construct the maximal independent set, and in the second phase we will connect them through a tree which is called a STNR tree, and we will also show that performance ratio of this algorithm is 8. The algorithm is message and time efficient also. Let us start with the algorithm that all the nodes are initially colored as white, the dominator is colored as black and dominantee is colored as gray. So there are 3 different colors we are going to use in this algorithm: white, then gray and black. Now we assume that each vertex has the knowledge of its distance 1 neighbors, and also they have another information which is called an effective degrees. That means how many number of white neighbors are there at any point of time is called an effective degree. Now this information can be collected by periodic event driven messages which are called hello messages. The effective degree of a vertex is the total number of white neighbor that I have already told. Now one of these host nodes we have designated as the leader. This particular assumption is also realistic, because if the leader is not, because leader can be a commander, mobile commander's mobile for the platoon of the soldiers in a particular mission. So, there is always a leader designated in such network and in many such applications. Now, if it is not designated, then we can designate using an algorithm which is called a distributed leader election algorithm. So, if we run the distributed leader election algorithm, it will take order n time and the number of messages will be n log n with the best known such available. So, hence, let us assume without loss of generality that a host S is the leader in the construction of CDS. Now, the phase 1 will construct the MIS. So, let us start with the leader node. S is the leader. So, leader first color itself as a black. Now, here this is the leader which will color itself as, let us use the black, while all other nodes are white. Now, this particular node will send a message which is called a dominator, because after becoming black, this particular node is called a dominator node. It will send a message which is called a dominator, and that will go in its all the nodes in its communication range, which is nothing but a disk within the disk. Now, any white node U, let us say this is the white node U, receiving the dominator message for the first time from a vertex V, it will color itself as a gray. It will color itself as a gray and broadcast a message which is called a dominity. So, it will broadcast. So, this particular message, when it will be broadcast, it will be broadcast in its communication range, and this U will select V as its dominator. Now, this particular white node, here they are the white nodes, when they will receive this particular message, they become active. The active white hosts with the highest effective degrees D star among all its active white neighbor will color itself black and broadcast dominator. Let us assume that this is the node having the highest degree, and it has colored itself as a black, and it will broadcast a message which is called a dominator. So, the white node decreases its effective degree by 1 and broadcasts message the degree whenever it receives a dominating message. The message degree contains the sender's current effective degree. A white vertex receiving a degree message will update its neighborhood information. So, each gray vertex will broadcast message number of black neighbors when it detects that none of its neighbors is white. So, phase 1 terminates when there is no white neighbors left. Now, we will begin the phase 2. Phase 2 is nothing but it will construct a STNR through a STNR tree. It will connect the nodes in MIS which we have obtained in the phase 1, and hence MIS plus the connectors will become a connected dominating set. So, STNR tree will be able to form a subgraph induced by the MIS nodes, and that will be the connected dominating set together. Now, when S receives, S here is basically the leader node, When leader receives the message number of black neighbors from all of its gray neighbors, it starts phase 2 by broadcasting a message M. So a host is ready to be explored if it has no white neighbors. A standard tree is used to connect all the black hosts generated in phase 1 that I have told. The idea is to pick those gray vertices which connect to many of the black neighbors. Why? Because we want to minimize the nodes in CDS. So that means with a minimum number of nodes we want to establish a connection, want to connect MIS nodes. Now we will apply a classical depth first search algorithm and that distributed version, that is the distributed depth first search spanning tree algorithm, to compute the state tree here in this particular phase 2 algorithm. Now a black node without any dominator is active. Initially no black vertex has the dominator and all hosts are unexplored. Message M contains the field next, which specifies next host to be explored. A gray vertex with at least one active black neighbors are effective. So M is built by the black vertex. Its next field contains the ID of unexplored gray vertices which connects to the maximum active black hosts. M is built by the gray vertex. Then the next field of ID contains the unexplored black neighbors. So either M is built by the black vertex or M is built by the gray vertex. So any black host receiving message M for the first time from the gray host sets its dominator to that V by broadcasting the parent message. So when a host U receives message M from V that specifies U to be explored next, if none of U's neighbors is white, U then color itself as a black, sets its dominator to V and broadcasts its own message M. Otherwise you defer the operation until none of its neighbors is white. Similarly, this particular process will follow for the gray neighbors. Now when there is no, when the gray vertices becomes ineffective if there is no black neighbor is active. So when there is no effective black neighbors remains, the gray neighbors becomes ineffective. Similarly for the black nodes. So when S gets a message done, that is it has no effective gray neighbors and the algorithm will terminate. Let us see this entire algorithm working through in this particular example. This is S, that is the leader node. So in phase 1 it will broadcast, first it will make itself as a black and broadcast message as a dominator in its one hop neighborhood. They will turn as the gray. So all the other nodes are turned as the gray nodes. These gray nodes will further communicate a dominating message in its neighborhood, and the white nodes who will receive the gray or a dominating, they become inactive. So this particular every white node will count how many active white neighbors are there, and the maximum one, for example having that particular value, will basically become black. So in the phase 1, when phase 1 will finish, it will basically form the black nodes and they are nothing but the MIS. Now in phase 2, when there is no white node left, then phase 2 will begin. Now phase 2 will be initiated either by the gray nodes. Gray nodes will inform how many black neighbors are there. For example, this is the gray node which has two different black 1, 2 and 3 different black nodes are there in its neighborhood. So it will inform to these particular black nodes using this particular message M. So this particular black node will choose this gray node and it will send a parent message. So it will establish a link between it. Now since this is the node which is having the maximum number of black neighbors, so this will in the phase 2 through the steiner tree, this will become a black. So this is the black node, that is the gray node having the maximum number of black neighbors will be basically elected as the connectors, or through the steiner tree it will be turned into a dominator. So when phase 2 will finish, then there will not be, that means all the black nodes will be having assigned a connector node through the gray node, and also there is no gray node which is having an active or an effective black node without any connection with its neighbor dominating sets or its neighbor MISs. Hence the algorithm will terminate with forming a connected dominating set, which is shown here with the black nodes. The complexity of the phase 1 and the complexity of phase 2 nodes, which we will see, the total of message and time complexity is given as of the order n, and message complexity is of the order n times big delta. Now let us see the performance analysis. Phase 1 computes an MIS which contains all the black nodes. Now another lemma says that in phase 2 at least one gray vertex which connects to the maximum number of black vertices will be selected. Now here in lemma 3.4 we will see that if C are the number of black nodes hosts after the phase 1, then it requires at most C minus 1 gray host which can be colored black in phase 2. Lemma 3.5 says that if there are a gray vertex which connects at least 3 black nodes, so the number of black vertices required is C minus 2. Therefore, if we check the performance ratio of this algorithm, in the phase 1 the size of the MIS is, let us say, 4 opt plus 1. Now in phase 2 we require, let us say, MIS size minus 2, that is plus 4 opt plus 1 and minus 2. These are the connectors. So total if we count, it becomes 8 opt. So 8 opt and this 1 and 1 will go out. So hence the performance ratio of this algorithm is 8 opt. More references on this you can find the paper by Rajiv Mishra, minimum connected dominating set using collaborative cover heuristic for ad hoc sensor network, published in IEEE Transaction Parallel Distributed Computing 2010. Conclusion: in this lecture we have discussed the algorithm, distributed algorithm for connected dominating set of smaller size. We have seen that this construction requires first to construct maximal independent set and then stay in a tree to connect all these vertices, and the performance ratio we have shown that it is 8. In future, scope of this algorithm is to study the problem of maintaining CDS in the mobility environment. Thank you.